Didn't see you there. Today we're talking about waves. Waves not only do not die, but they're also a periodic disturbance of particles of a medium. The waves may be propagated or transmitted without a net movement of the substance's particles. Examples of waves include sound, radio, string vibration, and internal water waves. As you can see, waves are all around us, and as you will learn, there's only one fundamental wave. Basic definition of velocity as displacement over time, or the change in displacement over the change in time. We have the tools to determine the speed of wave propagation. We know that a wave is periodic, i.e. it repeats after a fixed time interval, or period of time. In this given amount of time, it also travels a fixed distance, also known as its wavelength, denoted by the Greek letter lambda. Thus, we know that the velocity of propagation is equal to the wavelength over the period. We know that since v is equal to wavelength over period, rearranging, we get that the wavelength is equal to the velocity of propagation over the wave's frequency, since 1 divided by the period is the frequency of the wave. We organize it this way because usually we need to find the wavelength, because speed is not determined by wave frequency. We shouldn't just plug and chug with the equation, so let's educate ourselves a bit about wave before we tackle a problem. We should first go over that amplitude is the maximum disturbance of the medium. If we were to graph the wave's perturbation or displacement versus its distance traveled, we would see a graph like this, where amplitude is denoted A. We also know that velocity of propagation is determined solely by the medium and the material of the wave, while frequency is determined by what disturbs the medium, and it does not change through mediums. We should also go over that when two waves interact, there can be constructive interference, which is where two waves travel in the same direction, or destructive interference, where they travel in opposite directions. In AP Physics 1, we work only with transverse and longitudinal waves. Transverse waves travel perpendicular to their propagation, such as a rope when it's oscillated, while longitudinal waves travel parallel to their propagation, such as... Finally ready to tackle a waves problem. This problem says, given the speed of sound is 343 meters per second in dry air at 20 degrees Celsius, one loudspeaker produces a sound of wavelength 0.68 meters, while another one produces a sound of wavelength 0.65 meters. What would be the resulting beat frequency? Now, off the top of my head, I don't know what beat frequency is, but we can logically infer, since we know the two speakers' frequencies are going to be different with a constant velocity of wave propagation of 343 meters per second. We can calculate f of 2 is equal to 343 over 0.68, and this value is approximately 527 hertz. And f of 1 is going to be equal to 343 divided by 0.65, where f1 is equal to 504 hertz. Now, frequency is not necessarily a vector, but I can probably conclude that the two waves are going to undergo destructive interference, since sound waves will collide with one another while they're placed. We can assume frequency is a vector here, though, for practical matters, and calculate the difference between f2 and f1, which is about 23 hertz.